So up until this point, we have been considering electric fields and magnetic fields that are static, meaning they are not changing with time. In this lecture, we are going to move into dynamics where things are changing with time, and this is an important step to build us up into understanding how radio waves and electromagnetic waves in general work. And the first thing we're going to do is introduce Faraday's law, which is going to relate how time-varying magnetic fields are going to create some sort of electric field. So this will be in two sections. First, I'll introduce what Faraday's law is, and in part two, I'll talk about some applications of Faraday's law. So starting out with Faraday's law. All right, let's start out by reviewing the equations, the key equation that we have so far for electrostatics and magnetostatics. The first is what we call Gauss's law. Gauss's law told us that the divergence of the electric flux density lines D equals rho V, or the electric charge density at a given location, right? This was called Gauss's law. And it was a fancy way of saying that the sourciness or the sense of electric flux lines emerging from or converging into a location is directly equal to the amount of charge density that is present at a location. Another way to state this in words is that electric field lines, sorry, not electric field, that is electric flux density lines, start and stop, respectively, at positive and negative charge, electric charge, of course. All right. Now, there is a magnetic field equivalent of this that we could probably write out, since there are sort of nice analogies between electric and magnetic fields. So we can write the same divergence, except instead of electric flux density, we're going to put down the magnetic flux density. And on the right side, it'll be tempting to put something like magnetic charge, but of course there is no such thing as magnetic charge. So for that reason, we're going to put a 0 right there. That you could say that magnetic flux density lines start and stop at positive or negative magnetic charge, but since there's no such thing, we can simply say that magnetic flux density lines do not start or stop. Another way to say this is that magnetic flux density lines have to go in circles. That's the only way they can exist and not have a beginning or an end. All right, the other two basically are going to involve the curl or the swirliness of some vector field. And let's start out with what we called Ampere's law, which is that the curl of the magnetic field H equals the current density that's present. Right, current density J is amps per meter squared. It's the density of current per unit area. If I open up some window, then it's the density of current that's through that small little window. And this basically tells us that magnetic field lines are going to swirl around currents. Right, this is still statics. The current can be steady in time, it can be constant, and that's enough to establish magnetic fields around those currents. Now, the equivalent for the electric field, that the curl of the electric field equals something, our temptation to start out with is to put a 0 right there, right? Because since there's no such thing as magnetic charge, there's also no such thing as magnetic current, therefore there ought to be a 0 there, right? And this is correct for statics. But as we're about to find out, there is basically something missing right here that's going to be true for what we're going to call dynamics. Dynamics is where things are changing with time. And that is called Faraday's law. So let's first review what del cross E, or what the curl of E equals 0 means, and then we'll add on this new term that Faraday's law is going to give us. So what does it mean for the curl of the electric field to be 0? Right? And there is an example in the notes where if we have a very small box, And let's define the electric field on all four sides of this box. Right, and this is going to be the x component of E in the negative y direction. Let me define the axes here. This will be x and y. Right, this is the x component of E in the negative y direction. This would be the y component of E in the positive x direction, meaning with respect to the center of this box. This vector right here will represent the x component of the electric field in the positive y direction, but it's also pointed opposite to x, so we're going to have to put a negative sign right there since it's counter to x. And finally, we'll have a vector going down right here, which is negative E in the y direction, displaced a little bit in the negative x direction from the center of this box. And again, it's negative because it's pointed opposite to our defined y-axis. All right, now let's consider what happens if we have the integral of the electric field dotted with dl, and we're going to take a closed path, meaning we're going to start at point A, and we're going to loop all the way around to come back to where we started. Right, this integral here, and let's say each of these lines has a length of delta x. Right, if we calculate this integral, this will turn out to be equal to delta x times ex minus y plus ey plus x minus ex plus y minus ey minus x. All right, let's rearrange this. This equals delta x times ex minus y minus ex positive y minus ex positive y minus ey minus x. Sorry, I'm missing, rearrange this a little bit incorrectly. Let me just be consistent with the notes. This is ex minus y plus ey positive x. All right. What you'll notice is that this first term right here basically represents the counterclockwise components. Whereas these two basically represent the clockwise components. So in that sense, we can actually write this as a curl, right? Because the curl of E, it tells us to what degree things are swirling around. If the counterclockwise wins out over the counterclockwise, then we're going to have a positive curl. If the clockwise wins out, we're also going to have a non-zero curl in the other direction. But what we also know from our definition of electric potential, that the integral from any point A to B of E dot dl equals the electric potential at A minus the electric potential at B. This closed integral ought to be zero, right? Because we're starting out at a given location, we're walking around or coming back where we started, and we should be at the same electric potential. It's a little bit like altitude, right? If I stand somewhere, walk around, and come back where I started, I'm at the same altitude. So for that reason, we can start out by saying that the curl of the electric field equals E, and this is true for statics. And this is basically a required condition in order for there to exist something like electric potential that makes sense. Because if the curl of E were anything other than zero, that means I could stand somewhere, I could walk around, come back where I started, and I would get a non-zero total, which means that the altitude is not the same as where I started out. And that doesn't make sense. It sort of violates the idea of altitude as being something reliable. And so this is true for statics. What Faraday's law basically tells us, and Faraday's law was determined experimentally, is that the more complete way to write this is the following: that the curl of the electric field equals negative time derivative of the magnetic flux density. And this term right here is dynamic because it's a time variation. And this is what we call Faraday's law. All right, let's try to see what this means visually. All right, so let's say I'm going to draw a magnetic field line. Let's say it's pointed here. All right, this is the magnetic field at t equals 0. All right, let's say a short time later, the magnetic field line is pointed in the same direction, but it's shorter. Right, so this is the magnetic field line at t equals 0 positive, just a little bit later. Right, if we do that, then dB dt is going to be asking the question, by how much has the magnetic field line changed? Has the magnetic flux changed? And it's changed by that much. Right, this is the dB dt is going to be this vector right here. All right, this is dB dt. All right, Faraday's law is that the curl of the electric field equals negative dB dt. All right, so let's flip this vector around. I'm going to put a minus sign on the dB dt, and I'm going to have the vector point in the other direction from where it was before. All right, now this is negative dB dt. Faraday's law tells us that electric fields are going to swirl around that time varying vector, that time variation vector. And so the way we can determine that is take your thumb pointed in the direction of negative dB dt, and your fingers will swirl around in the direction of the electric field. This can be hard to draw over here, but it's basically, it's this, right? This would represent the electric field, right? It's going to swirl around that time-varying magnetic field lines, right? And that's basically what Faraday's law tells us. Let me just put this a different way so you can see how the directionality can work out. In order to separate the magnetic field from the time variation of the magnetic field, let's say that at t equals 0, this is our magnetic field, right? A short time later, we have a magnetic field that has the same vertical length, but we've now acquired a horizontal component to it as well. Right, this is t equals 0 positive. This vertical component is the same from t equals 0 to t equals 0 positive, but we've acquired a new component that's horizontal, that's this way. If that's the case, then dB dt will be a vector that points in the horizontal direction. And again, let's put that negative sign back and flip the direction of dB dt, like this. And now the electric field lines are going to swirl around that. So point your thumb in the direction of negative dB dt, and the electric field lines will swirl around that. So if that's the case, the electric field lines will be coming out of the whiteboard on this side, and it will be coming into the whiteboard on that side. Right, this is into, and this is out of. And these are the electric field lines. So that's Faraday's law, that electric field lines are going to swirl around the time variation of currents. Let's try to write this down a little more mathematically, though, and try to expand the definition of that curl. Right, so the curl of the electric field, we can write that as a three-dimensional determinant with x, y, and z on the first row. The second row, we're going to put the del operator, which is the derivative with respect to x and the x component, the derivative with respect to y and the y component, and the derivative with respect to z and the z component. In the third row, we'll put the three components of the electric field, the x component, the y component, and the z component. Let's expand this out. This equals x direction times the derivative of the z component of E with respect to y minus the reverse derivative of the y component of E with respect to z minus, in the y-hat direction, just make this a plus and flip it, dEx dz minus dEz dx plus z component dEy dx minus dEx dy. All right, so this is our expanded definition of the curl of the electric field. And now we're setting that whole thing equal to negative dB dt. So what we can say is that this is actually three equations relating each of the three components of negative dB dt. So this pair of partial derivatives right here is equal to negative time derivative of the x component of v. This pair of partial derivatives equals negative dby dt. And this pair down here equals negative dBz dt. All right, so in that sense, we actually have three equations that are encompassed by this Faraday's law, this curl equation. All right. Now, one of the lessons of this is that the idea of voltage is essentially no longer relevant when we have things that are varying. Right. The notion of electric potential, of voltage, is that I can stand somewhere and measure my altitude. I can walk around and come back where I started. Basically, I can take a complete path integral of where I started, and that's going to end up being zero. This is no longer the case, which means there's no such thing as potential. It doesn't make any sense anymore. If I walk around, come back to where I started, and I'm at a different altitude. Remembering that if electric potential is like altitude, then E is like the direction you have to go, north, south, east, or west, in order to have the fastest downhill motion. Then that's what the electric field would tell you. In dynamics, when you start changing the magnetic field with time, we essentially can no longer define electric potential. It doesn't make sense anymore. And that's going to be a little bit of a hint, because later on, we're going to actually do something to our Ampere's law equation, right? That the curl of H equals J. So we've established now that the curl of E is not equal to zero, but equals 0 minus dB dt. In the next lecture video, we're going to figure out something that's going to go in here in order to keep our duality between electric fields and magnetic fields functioning. All right. So let's talk for a second about what we mean by a curl, right? And one of the ways we can talk about what a curl means. So let's say, for example, we have a magnetic field that has the following relationship, right? That the magnetic field at any location x, y, z, and t is just defined in the following. So it's at any given moment, the magnetic field is constant with respect to time anywhere you go, but it is changing. Sorry, it's constant with respect to location, but it's ramping up in time, right? The magnetic field is constantly increasing in the z direction. So what would be an example of electric field that might satisfy Faraday's law? And I guess I'd ask you the question, is there only one that satisfies that? So think about that for a minute. Pause this video if you need to, and think through what you think the answer to this might be. What kinds of electric fields might satisfy this? So let me now show you a couple of examples of solution to this. And I want to emphasize that there's more than one. Here are two examples of electric field lines that have constant curl in the z direction. For each one of these, we can set a box here, and we can take a look at the z components of the curl, which is going to be equal to d y dx minus dex dy. Right, so let's take a look at this box right here, and let's ask the question, the y component of E, is it changing with the x direction? And so compare the vectors over here to the vectors over there, and you'll get that yes, they are in fact changing. Then ask the question, how is the x component of the electric field changing in the y direction? So that would be comparing the x component of E here to the x component right there, and you'll get that this is going to be a curl that's in the positive direction, or it's coming out of the board. Right? This basically represents the z component of the curl. We can see the same thing on the right. This is another example of a constant curl. I can draw a box right here. And let's ask the question, the derivative of the y component of E with respect to x. In this case, there is no y component of E. And so this first term is 0. Right? But the derivative of the x component of E with respect to y, so that's comparing the x component of E here to the x component there, you can see that there is a difference, right? Here I have a small positive electric field, and here I have a bigger positive electric field. So that implies dex dy is not equal to 0. But since dey dx does equal to 0, that implies that we do have a constant curl that we can see right here. All right, so that concludes this video right here. We'll move on to the next one in just a second.